Right, the topic of this section is spatial interpolation. So we're going to do kind of a broad overview of methods and techniques that are used to estimate values where you don't have values using measurements at locations where you do have values. Some of this is a bit of a review because some of these topics came up in earlier sections. Some of it is new. So this is fairly short. Again, this is one of our last topics in the course. Okay, so let's do a quick review of some density estimation. I included this here because some people think of this as kind of an interpolation method. So anyway, I wanted to cover that here. So some of these we've talked about already. Point density, basically you're calculating the density of point measurements within a given radius. So effectively you're counting the number of points in the radius and dividing by the area. So this is an example of like kind of a moving window-based analysis where you'd have a window, it would count the points in the window, take the count, divide by the area of the window, and they would hop across so that each cell is a window. So high values indicate areas where there are more points, and low obviously where there are less points or no points within like the given radius. You can do this both for points, where you're basically doing points per unit area, or lines, where you're basically doing length per unit area. You can also incorporate a weight. So for example, if your points were like buildings, you could use the number of residents in the building as a weight. So buildings with more residents, like an apartment building, get a higher weight than like single family homes would in the calculation. And in that case, instead of having your output be in units of something like points per area, it's really going to be in units of like residents per area, for example. So you can incorporate that, and you can also change the size and even in some cases the shape of the neighborhood. Generally, the larger search window that you use, the more general pattern you'll get, and the smaller search window you use, the more generalized or localized pattern you're going to get. There's not really a standard or way, or there's not really a right window size. It just kind of depends. So a lot of that just depends on the patterns that you're interested in, similar to making a kernel density plot. Again, we also talked about kernel density. Kernel density is similar to point density, but it uses this like quadratic function where a lot of the weight is placed closer to the center of the search radius and tapers as you move out to the margin of the search radius, as opposed to the weights or being homogeneous within the search radius. But it still basically gives you the same output, which is an estimate of density of point measurements. So in this case, this represents the density of structures for counties up here in kind of the north central West Virginia area. Again, this is basically like a kernel density plot, but in 2 dimensions as opposed to in 1 dimension. So again, the units here are going to be points per unit area. If you use a weight, like again, if you're doing houses and you use the occupancy at the houses, it would be in people per unit area. It's different from point density because you're using a quadratic function where the weight tapers towards the margins of the window as opposed to being homogeneous across the window. Generally speaking, I tend to use kernel density as opposed to using point density. Just depends on the use case and whatnot. This slide just explains that in a little bit more detail if you're interested. And there's a video about density calculations. Okay, spatial interpolation. So first off, what is spatial interpolation? Like, what's the goal? So a lot of times we want to be able to estimate a value at a location when that location actually hasn't been surveyed or measured or whatnot. So generally what we do is we use the measurements that we do have to make predictions at locations that we don't have measurements. There are generally 2 kind of broad situations where you're making an estimate at a new location. One is known as interpolation, and that is signified here by this blue star. So this is making a prediction within the geographic bounds of your data, right? So that's our extent. The x falls within the bounds of our samples. In contrast, extrapolation is generally when you're making a prediction outside the bounds of your data, and that's symbolized here by the yellow star. So this is extrapolation, and this is interpolation. Since there are no samples around this, we're basically using these values to extrapolate over to this location. So that's generally considered to be more dangerous or more uncertain than interpolation. This is also true like in a graphic space. So here we have a bunch of measurement points that show that represent a relationship here. And sorry, we plotted a line through them that represents a relationship between our x variable and our y variable, right? So note here that we only have measurements in this range. Outside of this range, signified here by these lines, we don't actually have any measurements. So in this area, we generally could assume that this line is more representative of the relationship between these two variables than if we move outside of that range, since we don't have any measurements. So for example, maybe this actually like levels off after a point, it's no longer linear, or maybe it like kind of explodes and becomes more like exponential. Maybe same thing happens down here, it could level off or it could dive, right? So again, extrapolations are considered more uncertain, less accurate than interpolations. But note that no matter what you're doing, extrapolating or interpolating, you are making an estimate at a location that you haven't actually made a measurement, so there is some inherent uncertainty or error associated with that, but it's not always easy to know or quantify. Okay, so now what we're going to do is step through some general methods that are used to make estimates where you don't have measurements. Thiessen or Voronoi polygons we already talked about in the context of vector-based spatial analysis and geoprocessing. The idea here is to find the area that's closest to one point than any other point. So in this data set, all these points represent meteorological or weather stations in Ontario. So for example, all the area here is closer to this weather station than it is to any of the other weather stations represented by black dots. So this is an interpolation method, because basically what you can do once you have these areas broken up is you can assign the measurement associated with that point to all the area that's closest to it. So basically all the locations or cells or whatnot within that extent would get the weather data that was collected at that observation station as opposed to one of the other observation stations. If you think about it, this is basically like a nearest neighbor type interpolation. So you're not averaging multiple measurements, you're just simply taking the value that's closest to that new location. You may think that this is very simple, and it is, but note that this is practically used. So for example, when people are doing like water balance equations, estimating precipitation, it is common to use Thiessen polygons or Voronoi polygons as a way to take your point measurements and get an aerial estimate of, say, runoff or precip or something. So it is very simple, but it is used. Excuse me. Okay, the next method that we're going to talk about is new, and this is inverse distance weighting, or IDW. The idea here is you're taking an average of to come up with a measurement at a new location. You're taking an average of all the measurements that of nearby measurements, but you're doing it in such a way that the measurements that are closer to that new location take a higher weight than the ones that are further away. And there's a couple different ways that this is implemented, and they can have different settings. So one is the power. So this controls the significance of surrounding points. If you have a high power, that means you're going to have a high coefficient, so the influence of points is going to taper off quicker. So the closer points are going to have a much higher weight than the points that are further away. So imagine like if you're looking at this in like 2D space, this is the new location that you're trying to estimate, and you've got some measurements around. Basically, this would be like the weighting, maybe it would be something like this with a higher, well, let's do say this was our lower power, and then for a high power, maybe it would be something more like this. Right? So it puts more weight closer to the near measurements as opposed to ones that are further away. The radius has to do with how far out you'll look to find nearby samples or measurements that you use to actually predict that new location. A variable, it means that you don't specify a distance but a number of points. So basically you can look out as far as you want. You say you just want to use the nearest 12 points. So you just go out and find 12 points, the nearest ones, it doesn't matter how far away they are. In contrast to that, fixed basically means that you're going to use all the points within a given radius. Note that when you do use variable, you can set a maximum distance. So if you don't find, say your number of neighbors is 12, if you don't find 12 neighbors within, say, 100 meters, then you're just going to use the ones that you did find within 100 meters. And fixed, you're basically using all the points within that fixed distance. Note that you can specify a minimum number of points that is used to increase the search radius. So if you don't find X number of points within a given search radius, then you can expand the search radius to incorporate more points. All right, so this is showing the inverse distance weighting tool in ArcGIS, excuse me, inside of ArcGIS Pro. So here's our input set of points. This is the measurement that we're wanting to interpolate. So it's, in this case, it's bathymetric measurement, so it's depth. This is the name of the output raster grid. This is the cell size. And then these are our settings for how we're going to actually implement our inverse distance weighting. So we're using a power of 2. Again, the higher the power, the faster the weighting tapers off with distance. We're using a variable search radius. So it's not a fixed search radius. We can look at as far as we want. And we're going to use the nearest 12 points. And we're not setting a maximum distance. So it can look out as far as it wants to find those 12 points. So effectively, for every location, it's going to find the nearest 12 points, regardless of how far they are away, and it's going to take an average in such a way that the nearer points have a higher weighting than the ones that are further away. So that's inverse distance weighting. Another common way to do it is using what's known as a spline. Spline are generally used when you want to have more of like kind of a gradual or smooth surface than what you would maybe get with an inverse distance weighted method. But it kind of depends on the data. Okay, so here's kind of a conceptualization of spline. So imagine you have, again, like we'll just do one-dimensional space. So you can kind of extrude out all of your point measurements to a height that represents the magnitude of the measurement that you're interpolating. So this height would represent the magnitude of the thing that you're trying to estimate. And then you basically are kind of like fitting a rubber sheet in two-dimensional space, or you could think of it as a line in one-dimensional space, through these points, but it has a little bit of there's some limits on how much it can bend, right? So you're basically trying to pass through the points, but you're going to have some limits on the amount of curvatures of the surface. So basically the more curvature you allow, the more complicated or less smooth surface you're going to get. So it's basically going to try to warp this surface as much as possible to capture all these measurements. Whereas if you allow for less curvature, then you're going to get a more gradual representation of the pattern. So basically the idea is to fit a mathematical function to a specific number of near points while passing through the sample point. Surface passes through sample points and has a minimum defined curvature. Again, this is generally not a good method to use if you have a phenomenon that could change very abruptly, because it's going to try to generate kind of a smooth surface. That's a quick overview of spline. We're going to get into it in detail. Note that spline is used in other contexts, like it's used in like linear relationships, and there's like spline incorporated into like generalized regression and whatnot. A general thumb for me again is if I'm doing interpolation, I only really use spline if I want a smooth surface. I tend to use inverse distance weighted more personally. Okay, in the last section of this, we're going to just do a quick general introduction to Kriging, which is a more complex geostatistical method to do interpolation. It has some other uses too. Again, if you took a spatial stats or spatial modeling class, you would maybe get into Kriging in much greater detail. Here, our goal is to just simply introduce it. Okay, so Kriging has basically two general components. So in order to make an estimate at a new location, you're basically going to model a general global trend by using the existing data points. And then you're going to try to improve that model at the local level by incorporating spatial autocorrelation. So it has this sort of like simple global model, like fitting a polynomial to a distribution, and then an improvement, hopefully, of that model by modeling and incorporating modeling and considering local spatial autocorrelation. So you've got your global trends and your more local spatial trends, more local autocorrelation trends. So the first thing is a global trend. So you generally want to find a function that kind of approximates, again, the global trend in the data. So it could be like a linear trend where it's kind of increasing or ramping in one direction. It could be like a polynomial where it's like kind of bends in one direction or multiple directions. But it's basically going to be a fairly simple mathematical pattern. So for example, we can see here that this kind of just increases as this is, what is this? This is temperature, I believe. So you can kind of see a pattern where it's just kind of increasing as you go south and increasing a little as you go east. Where in contrast, this is ozone in California. So you can see it kind of increases kind of in the middle of the data set, decreases towards the margins. Okay, so that's the first stage, is to fit this local trend. So this is showing this ozone measurements in California. So I kind of fit this using like a polynomial. So it kind of increases towards the middle and tapers towards the margins in two different directions, and has a bit of a directionality to it. Once you do that, then you're going to you're going to use the semi-variogram to assess how you want to incorporate local spatial patterns to improve the model. And that you can do using a semi-variogram. We don't need to really discuss semi-variogram in detail, I don't think, because we did in the last section. Again, a quick summary. Again, each point represents a pair of measurements. The x-axis position is the distance between those two measurements. The semivariance is basically the difference between them squared. The CIL is the value of the semivariance where the pattern levels off. The distance at which this levels off is the range. And then we have that nugget effect, which has to do with like measurement error and spatial scales, where you maybe don't get a zero semivariance at a distance of 0. So in order to incorporate this spatial autocorrelation, we use the semi-variogram to get a sense of the distance at which we want to kind of stop considering spatial autocorrelation. Again, that just goes into that in detail, just like the last section. Okay, so that's that. And then lastly, you can have anisotropy. I can't say that word. Anisotropy. So this is when the spatial dependency or the spatial autocorrelation isn't consistent in all directions. So you might have a directional trend in the autocorrelation. So tools for fitting Kriging models generally have an ability to do that and to have a directionality applied to it, not just be homogeneous in all directions. Okay, so that's it. So then basically once you've incorporated your local autocorrelation to your global model, you get a much more complex trend here that hopefully captures more of the variability in the data. So this is kind of the steps to doing Kriging. So you want to explore statistically explore the data, look at the semi-variogram, create a surface, and explore the resulting output and variability. This is important. So Kriging is most appropriate when you know there's a spatial correlated distance or directional bias in the data. So whenever there is spatial autocorrelation, and also if there's spatial autocorrelation with a directional pattern, then Kriging may be a better option than simply using like inverse distance weighting or fitting a simple mathematical function to the data. So some things to consider is, since it's based on this like statistical analysis, it's good to look at your data distribution to determine how far it is from normal, whether there's issues of skewness. So like this, for example, maybe has a tail towards high values. So if you kind of fit a curve like something like that, so it's got a bit of a high tail. Again, here's our QQ plot to look at normality. Again, this kind of has a bit of a concave shape. So maybe this again kind of relates to having a skew to the right. Kurtosis again is how light or heavy tailed it is relative to a normal distribution. So anyway, you can look at the data normality. In some situations, it might make more sense to model a transform version of the data that's more normal than the raw data points. Consider what type of function actually specifies or would capture the general global trend. So whether it's like a plane increasing in one direction, or some type of polynomial type surface, or more complicated surface. And then try to improve that model using your semi-variogram. So this is a semi-variogram plotted with this geostatistical wizard tool in the Arc desktop, right? So you could kind of maybe get a sense of where the distance at which the autocorrelation is not much of an issue. Again, this is real data, so it's not as clean as our hypothetical data we saw in our hypothetical semi-variogram. And again, another thing to consider is whether that pattern is consistent across space or whether there's a directional trend to it, which you can look at with the semi-variogram analysis. So some things to generally consider. One, is it a good idea to transform the predictor variable in order for it to be more normal? So maybe like taking the square root or the log or something of it. Considering the sill range and nugget from the semi-variogram in order to incorporate the local spatial patterns. Is there a directional trend? And the best search direction and width for your incorporation of local patterns. Kriging also can provide an estimate of error, right? So here you can see this is the prediction, this is the model output for ozone, and we see a higher error term generally the farther we get from the data points and towards the margin of the model, where there's less data points to actually control or parameterize the surface. Excuse me. This can generally be implemented using the Geostatistical Analyst wizard in ArcGIS Pro. So there's tools for doing Kriging and some other spatial interpolation methods. Just as a side note, code Kriging basically allows you to incorporate a covariate into the analysis. So instead of just using the patterns of points, both their global pattern and the local spatial autocorrelation, you can have another variable that is incorporated into the model to potentially improve it. So for example, you may, if following ozone, maybe you find that elevation matters, so you could incorporate elevation as a covariate into the model. All right, and that's it. So this is supposed to be just a quick, brief introduction to interpolation techniques. So we did a review of some of our point pattern summarization methods, point density, kernel density. We also talked about line density. We looked at some fairly simple ways to interpolate or guess values at new locations. So Veroni or Thiessen polygons, the IDW and inverse distance weighting and Spline. And then I did a brief introduction to Kriging and co-Kriging as a more complex geostatistical method that incorporates both global trend and local spatial autocorrelation.